Good afternoon, everyone. Welcome to the 11th tutorial session in the subject Design of Steel Structure. I am Subrani Karmakar. I am a PhD student in the Department of Civil Engineering uh, at IIT Kanpur. So today we will be taking up, we'll be continuing the topic which we started in the last week, that is design of uh, vending language, like designing of beams. And within that, we had understood uh, what is a laterally supported beam, what is a laterally unsupported beam. And uh, so we designing certain members of these in like a purlin. What is a purlin? A purlin is designed as a continuous beam. So how will you design a purlin? Then one more example which we'll see. Suppose uh, the section which is available to you, or you have certain restrictions on the depth, and you have to accommodate the section within that depth only. So, but you have a higher demand of plastic section capacity. How will you achieve that? How will you, like, basically, you need to attach plates to the section in order to increase this plastic section modulus. We understand how do we calculate plastic section modulus. And then I'll also try to touch upon gantry girder or time focus. Otherwise, we'll take that topic next week. So, So first, we'll look at an example. I'll take up a channel section, and then we'll try to understand. Take up a channel section, and we'll find out the plastic section modulus about the major axis and the minor axis. So let's do it in the form of a question. Determine the plastic section modulus about the strong and weak axis, about the strong and weak axis for um, bended channel section. Plastic section modulus is ZP, which you require uh, in the while calculating the design bending strength. Uh, and we had discussed that clause in the previous class. I've shown you that clause for my 800 to 307. So suppose my section is something like this. Okay, so I want to find out the plastic section modulus of this welded channel section. So let this be where this is H, W, this is TF. So first we'll find out the plastic section modulus about the strong axis. First is strong axis. What do you mean by strong axis and weak axis? So you can find out the moment of inertia, like about the major axis and minor axis. So moment of inertia about the major axis is more than the minor axis. By strong axis, I mean the major axis. This one, clear. I think so. Yeah. So this is the major axis, and for plastic section modulus, we need to calculate the equal area axis. So an axis which divides the section into two equal halves. So we know that for the channel section, this this axis is the axis of symmetry. This is the axis of symmetry, like that is the centroid. Uh, this axis will pass through the centroid of the section, and this is also the equal area axis because area above the axis is equal to area below axis. So for this section, let's take this portion. For this portion, what is the height of this portion? The height of this portion is will be h. H is the total height, so this will be okay. Let's take this area. The height of this area will be the total height h by h divided by 2. That is the upper half minus th. I hope this is clear. And where will the centroid of this portion lie? The centroid of this portion will be at this portion. That will be h by 2 minus tf divided by 2. And centroid of this upper half, where it will lie. Centroid of this will lie at h by 2 minus tf by 2. So basically h minus tf by 2. And this centroidal position. This will be at a height of this centroid. This will be h by to make it a bit legible. This height will be h by 2 minus tf. So with this data, we can find out the plastic section modulus about the weak axis. Let's call this the ZZ axis. This is the equal area axis. So ZPZ is equal to, it will be how much is the stop area, like this area which I shaded with that orange color. It will be, the area will be TF into BF, fine, into its centroidal height, which is H minus TF by 2. The distance of the centroid from the equal area axis. That is this distance. Okay. Plus the area of this position, which this highlighted part, which is H by 2 minus TF, into the thickness is TW, into its centroidal position, which is H by 2 minus TF by 2. Okay. This was one more term. Now, since the section is symmetrical about the equal area axis, uh, so the centroidal position here will be same as that of the portion above. So basically, this number will simply become 2 times. And if you simplify this, you will get BF into TF into H minus TF plus TW times H by 2 minus TF. So this is ZPZ about the weaker axis, the plastic section modulus about the strong axis. Now we'll have to find the plastic section modulus about the weak axis. Now, you don't know the about the weak axis, means about the this being the ZZ axis. Suppose the YY axis is somewhat in this direction. Now I don't know the position of equal area axis. So first we'll have to figure out that, and then you can calculate the plastic section modulus. So we'll consider two cases. See, since I've taken a very generalized section with, I've not put the dimension numbers, so let's consider two cases. First case, when the equal area axis lies within the web, and one when it does not lie in the web. So let's consider the case when the equal area axis lies within the web. So let's consider the equal area axis lies like this. It is lying within the then, and suppose this distance is z bar, Fine. Suppose this distance is z bar. Fine. Then we can write for calculating the equal area axis. Let's first write the area which is on this side. So how much is this area? This area is h into z bar and equated to the area on the right hand side, which is h times how much is the remaining uh, tw minus z bar. This is one term, and the two flanges which are left, which is bf minus tf. Okay, that into tf times. So from here we can calculate the value of z bar, and we'll get the value to be h into t bar. I'm not simplifying the entire expression here. Like you can try it later on. I'm just putting the result directly into tf and tew into tf by 2h. This is the value of z bar. Once you know the value of z bar, then you can easily calculate zpy. How will you calculate it? zpy will be, it is basically, the z is basically area into, now here will be uh, z1 bar plus z2 bar. Basically, the area of the section of, like, the area, should not call it section, the area of the portion multiplied by the distance of the centroidal distance of that portion from the equal area axis. Like here, it will be for the portion on the left hand side of the equal area axis, you have the area h into z bar. I'm writing it in terms of z bar, and its distance from the, this is the equal area axis here, equal area axis, the distance is z bar by 2. Fine. Now for portion on the right, since it's not uniform, let's break it into rectangles. So the first rectangle, it is this. Let's consider this part. What will be the area? The area will be tw minus z bar. This is the thickness into the height is h into the centroidal distance, which is tw minus z bar by 2. Fine. Then we have um, the two remaining triangles, which will be, first I'm writing for one triangle. The area will be BF minus TF. Okay, this is the this is the area. Fine. Multiplied by its centroidal distance, which is BF minus TF by 2 plus TW minus Z bar. This is clear. See, basically, centroid will lie something here. You need to know this distance. So it will be this small distance plus this distance. Now this distance we already know is TW minus Z bar. And how much is this distance? This will be BF minus TF. That is the total length by 2. This 2 I'm adding here. And since there are two two rectangles here and here, it will be 2 times. This is the expression for ZPY. Now, if you simplify this, you will get ZPY as h z bar square by 2 plus TW minus z bar whole square h by 2 plus 2 into but I'm recording the session. Okay. df minus dw into df df minus dw by 2 plus dw minus z. This is that. Now suppose the equal area axis lies outside the web. Then what will happen? Let's consider that case as well. So this was for the strong axis, and here we start the weak axis. Within weak axis, this is case 1, and weak axis raised to So now what I want, let the the equal area axis pass through here. This is the equal area axis. If this is the equal area axis, again I can find out the position of its position. Then let this be z bar. If this is z bar, then how do I write the area? So, let's first write the area to the left of this equal area axis. It will be h into tw, fine, plus 2 times thickness of the flange. H into tw means first term is this is gone. Now these two rectangles, uh, how much is its width? It will be z bar minus tw. This is done. Now the area on the right hand side means this area and this area. It will be 2 times because there are two rectangles into df minus z bar into df. When you solve this, you will get z bar to be equal to 2 df df plus 2 df dw minus h times dw by 4. Now I want to write zpy. So first, let's consider it for the areas on the left-hand side of the equal area axis, and then we'll consider it for the area on the right-hand side of the equal area axis. So h into tw is the area, and what will be its distance from the equal area axis? Z bar minus tw by 2. This is straightforward. Then for the for this rectangle and this rectangle, what will it be? It will be first 2, because there are two rectangles. Then the area. Area is z bar into tw into tf into its centroidal distance. What will be the centroidal distance? The centroidal distance will be Z bar minus TW, half, half, half of that. So that is done. Now for the area on the right side of the equal axis. Area is this term. So let's VF minus Z bar into TF. And what is its central distance? BF minus Z bar by 2. So on simplifying this, you'll get ZCY. So I hope this concept of calculating plastic section modulus is clear. Uh, so in the lectures you had, I think so you have seen how to do it for ice. And here I've shown do we uh, how do we calculate it for a channel section. Then let's do a question on designing for So, the question reads is as design an I-section purlin for an industrial building situated in a certain place. Okay. I will be giving you the wind intensity and all. Like basically, why is the location specified in such question? Because you need to know the design loads, and here these purlins are subjected to wind pressures. So we have to pick up this value of wind velocity from IS 875. I guess it's part 3. From there, you need to pick up this wind velocity value. So that is why the position is mentioned in such questions. And basically, you have to design a I-section purlin to support a galvanized corrugated iron sheet roof for the data, and the data is given. So design an I-section purlin to support a galvanized corrugated iron sheet roof for the following data. So spacing of the track center to center is 6 meters. Spacing of not spacing. Span of track 12 meters. Slope of track 30 degrees. Spacing of purlin center to center is 1.5 meter. Intensity of wind pressure intensity of wind pressure is 2 kilonewton per meter square. Weight of galvanized sheet 130 kilonewton per 130 newton per meter square. And grade of steel is Fe410. So this is the data which is specified. So basically, this uh, this is basically an industrial building. So it will be like this. A trough will be there. One more truss will be there. In between, one more truss is there. So spacing, this spacing, 6 meter. This is the truss. And here, span of the truss is 12 meter. Means this distance is 12 meter. Then slope of the truss is 30 degree. Means this angle is 30 degree. Spacing of purlins. Purlins is placed here, here. So the spacing of purlin is 1.5 meter. And intensity of wind pressure is given. Weight of the galvanized sheet is given and grade of sheet. So let's design this purlin. This is nothing but the purlin. The purlin will run throughout and it will be designed as a continuous beam because it is supported here, here, and here. So basically, it is a continuous beam of this sort where these are the supports. This, and this are the support, and it is subjected to wind load and basically it is subjected to dead load and wind load. And here, the weight of the galvanized sheet is given, means the dead load has been specified, and the wind pressure has been specified. Uh, this weight of the galvanized sheet is 130 Newton per mm square. Now, on one beam, how much weight is coming? The effective area just this much. So basically, uh, how much will be this length? It will be 1.5 meter. So the weight of galvanized, this is not right. Okay, that's right. Fe 410. So Fy will be 250 M. It one straightforward information. Corrugated iron sheet. How much is the intensity? 130 Newton per mm square. Newton per meter square, sorry, into 1.5 is this width is this width is 1.5. So that comes out to be 195 Newton per meter. And let's assume that the self weight of the purlin is some 100 Newton per meter. This I am assuming the dead load of purlin is some 100 Newton per meter. So what is the total dead load? And the total dead load acts vertically downward because in the direction of gravity, dead load is acting. So total dead load is 195 plus 100. So this much Newton per meter, which act vertically downward. Then is suppose suppose it's the dead load. This angle is 30. Then this angle is also 30. So component of the dead load parallel to the roof and perpendicular to the roof. Suppose the dead load I am this is 295 Newton per meter. How much the will the component be parallel? It will be 295 sine 30 and this will be 295 cos 30. I hope this is clear, sir. This is for the dead load, which we have understood. This comes out to be some 147.5 Newton per meter, and this comes out to be some 255.47 Newton per meter. Okay, this is really. Now we have to concentrate on wind load. So this wind load is acting normal to the roof, meaning wind load is acting in this direction. This is dead load. Now we have to find out the intensity of the wind load. So wind load is what is the intensity? See, the intensity of the wind load is 2 kilonewton per meter square, means this much Newton per meter square. Fine. And what is uh, the for one purlin? What is the area? We can call it the influence area, or like for the sheeting, what we had considered. What is uh, Yeah, let's call it the influence area. The width of the influence area is 1.5 meter. So this comes out to be 3000 Newton per meter. So this is calculated. So what is the total load on the purlin normal to the roof? So in the normal direction, you have 255.47 and this value. And we have to apply a factor of 50. So let's factor it as that. So total factored load normal to roof factor is 1.5. So 3000 plus 255.47. 255.47 comes from here. And this will get to be 4883.20 Newton per meter. And factored load, total factored load, which is along the roof. Along the roof is only this 147.5 Newton per meter, and let's factor that as well. So total factored load parallel to roof, which is 1.5 into 147.5. It comes out to be 221.25 Newton per meter. Okay, let's call this as P. Let's call this as H. Now, maximum moment due to this load P will be PL by 10 because it is continuous beam. So that is why this number comes. So, and suppose an I section is placed here like this. So when load is normal, this it's linear. So this will be the major axis, this will be the minor axis. So because of the factored load normal to the that is when the load is along the VP axis, the pending will be along the UU axis. So UU will be because of the load uh, parallel to the VV axis, that is due to load P, that will be PL by 10. Value of P is 4883.20. What is the length of the member? Like as I explained, the length of the purlin is this 6 meters into 6 by 10. This will be an okay. This P is the total load. So this is P into L is 6 divided by 10. Let's divide it by 1000 to like basically this load was in Newton. So to calculate it into kilonewton, I'm dividing by 1000. You'll get the number 17.6 kilonewton meter. Now MVV, this MVV, or the bending about the VV axis, bending about this VV axis, then the load will be along UU axis, that is load parallel to the root, that is H. It will be H into L by 10. What is the total H load? H 221.25. This is, I should not write here P. Let me call this small p and small h. So from here, capital P will be small p into the length, capital H will be small h into the length. Length being the length of the cord into 6 is the total h into the length of the member 6 divided by 10 into 10 to the power 3 for converting the load into kilonewtons. Like basically, yeah, I hope you get the idea. So 0.796. Now you have the two moments. So individually, we need to check whether the I section, which you are selecting, whether that I section can take up these moments or not, MUU and MBV. And then finally, we'll do an interaction check as well, because both these loads are acting simultaneously. So within that intersection check also should be same. So for selecting a section, a thumb rule has been suggested in the lectures as well. I'll be using the same idea. So let's try to use a section which has a flange width of 75 mm and a depth of 150 mm. And from there, we get an idea about how much plastic section modulus is required. So ZPZ required. Here I'm using that formula, MZ gamma M0 by Fy plus 2.5 D by df, then My gamma M0 by Fy. So MZ, or the major axis moment, is this, which is 17.6 into 10 to the power 6 to convert it into Newton mm. Gamma M0 is 1.1 by 250 plus 2.5 into B is 150, B is 75 into My, this is My, that is the moment about the weaker axis, 0.796 into 10 to the power 6 into gamma M0 is 1.1 by 250. So ZPZ required comes out to be 94.85 into 10 to the power 3 mm. So from the section handbook, that's the specific, you need to select such a section which has the plastic section modulus about the stronger axis equal to this or greater than this. So let's select ISMB 150. Now let's select ISWB 150. Okay. So we are selecting ISWB 150 at the rate of 166.77 ton per meter. And now I'll list down the sectional properties. Area is equal to 2167 mm squared. H is equal to 150 mm. GF is equal to ZMM. F is equal to 7 mm. TW is equal to 5.4 mm. R1 is equal to 8 mm. So what is the depth of the web? It is the total height minus 2 times thickness of the flange plus root radius. If you do the math, you will get 120 mm. Moment of inertia about the z-axis is 839.1 into 10 to the power 4 mm to the power 4 newton. Y is 94.8 into 10 to the power 4 mm. Z is 126.86 into 10 to the power 3 mm. Ez is 111.9 into 10 to the power 3 cube. ZEY is equal to 19.2 into 19 into 10 to the power 3 meters. Now, the grade of the steel is Fe 410. So we know epsilon is equal to under root of 250 by Fy is equal to 1. I want you to classify, this is the section properties. You need to classify the section and you need to tell me whether it's a flat section or compact section or semi-compact section. I'll give you time about 2 minutes. You need to tell me whether the section is, you need to classify the section. So for classifying the section, you need to find out the ratio of the width of the plate to the thickness of the plate. Like plate being in an I section, what are the two various plate sections? The flange, the outstanding part of the flange that can undergo local buckling. So you have to check it there. The web can buckle. You need to check it. So one ratio is B by TF. What is the B? B is the outstand of the flange, which is BF by 2 by TF. BF is 100, so BF by 2 is 50. And thickness of the flange is 7. So this comes out to be 7.14. And we know that the limiting value for a plastic section is uh, 9.4. So it's less than 90, meaning that the flange is plastic. Then we need to check it for web as well. D by TW. D is 120, TW is 5.4, which comes out to be 22.22, which again is less than 84. So it is plastic. So the overall section is plastic. So once you know the section, like from here, the normal beam design starts. You do the section classification. If you find it is plastic, then uh, you can calculate it design bending strength. Why do we need to do the design bending strength? Because depending on that, the factor beta B, the value is different. Like for plastic and compact, beta B is 1, and for basically in plastic and compact sections, you can use the plastic section. And for semi-compact section, since uh, that kind of sections can't develop the plastic moment capacity, it can see, the plastic sections can develop the plastic moment capacity, the plastic, yeah, plastic moment capacity, or what do I call it? The design bending strength. Using the term design bending strength will be wrong. Uh, Plastic sections can develop the plastic moment and show a certain level of ductility. For compact sections, it can reach the plastic moment capacity, but it will not have, it will not show that amount of ductility. Means, or in other words, the rotation at that plastic hinge will not be significant rotation about that plastic hinge will not be possible. But for semi-compact section, it cannot reach this plastic moment capacity. It will reach only the yield moment and then it will undergo local buckling. So that is why while calculating the semi-compact section, you have seen that beta B value in IS 800, it is ZE by Z. So basically, you are using, then you are multiplying it with ZP. Basically, MD is beta P ZP Fy by gamma V. When it is plastic and compact, this beta B is equal to 1. If it is semi-compact, beta B is ZE by ZP. So here you have ZP Fy by gamma n 0. So basically, you are calculating the moment with ZE, that is the elastic section modulus, because the section can develop only the yield moment, or the, let's call it the yield moment, or where the fibers in the section are stressed to the yield stress level. Or like what I wanted to say is, if this is the section and it is subjected to a moment, then the bending stress diagram will be something like this. And in the farthest fibers where the maximum stress is getting developed, this will be equal to Fy and this will be S in semi-compact section. Okay, I had deviated a little bit. So So now I will check for the design bending strength. Check for design bending strength. So MdZ is equal to ZpZ Fy by gamma n0. Why? Because the section is plastic. Now ZpZ of this section, it has already been mentioned. It is 126.86 into 10 to the power 3. 4. 126.86 into 10 to the power 3. Fy is 250 by 1.5. It is 28.83 kilometer meter. And we know this should be less than 1.2 times ZE times Fy by gamma m. So ZE and is the value of ZE. ZEZ is 111.9. 111 into 10 to the power 3 into 250 by 1. So this is 30.5 kilometers. So MdZ is equal to this 28.83 kilonewton meter. And how much moment is coming on the section due to the load? This 17.6 is coming. Now this value is greater than 17.6. This MdZ is greater than 17.6 meter. So the section is fine. Now we'll have to do it for the this is for the major axis. Now for the minor axis as well. So we have to check for MdY. MdY is ZEY Fy by gamma epsilon. And now I don't have the ZPY for this section. Do I have it? No. Why don't I have it? Because the value is not given enough. You will have to calculate it. So let's calculate the ZPY for this I section. Now, I section looks something like this. So we know the equal area axis will pass through it. Since it is a symmetrical section, you know, the centroidal axis will be same as the equilateral axis. It will be how much this is. How much is section? We have the depth of the section 150. The width of the flange, this is 50. The thickness of the flange is 7 mm. Thickness of the bed is 6.4. How much is the depth value? This depth value is 120. Yeah, these are the numbers which one. Let me why begin. First we take area. How much is the area? 150 into half of the web width, 5.4 into 2 into this centroidal distance plus the two rectangles, this rectangle and this rectangle. So 2 into how much is the length? Length will be 50 minus 5.4 by 2 multiplied by the centroidal distance. Let's write it like that and continue it here. First two, since there are two triangles, length is 50 minus, by length I mean this number, is 50 minus 5.4 by 2 multiplied by its centroidal distance, which will be from this to here. It will be this 50 minus 5.4 by 2 by 2 plus 5.4 by 2. And this entire number two times of s, since uh, uh, like because of the definition of that's the one. This comes out to be 34.203 into 10 MMQ. So we know that is y, which is 34.203 into 10 to the power 3. Fy is 250. Divided by 151 and this factor of 10.6 there. This comes out to be 7.7 kilonewton meter. Then you need to check this number as well. 1.2 ZE divided by gamma and 0. So ZE, ZEY is there, 19 into 10. This number should be less than 1.2 times ZE Fy by gamma and 0. That is 19 into 10 to the power 3 into 250 by 1.9 10 to the power 6 to be 5.18 kilonewton meter. So here you get 7.77. Here you are getting this. So that in dy is 5.18 kilonewton per meter. And this number should be less than mvv. Here mvv is 0.8. I can write it as 0.8. 0.8 kilonewton. Now we'll have to do the interaction. So check for overall member strength. Z by md z plus my by md by is less than equal to 1. 3.8 by 28.8 so 5.5 into 0.8. How much does it? 0.76, which is less than 1. So this section is fine. Then finally, we'll check for the so for this deflection check, this is the serviceability check. So serviceability check, uh, what load is used, factored or unfactored. For the limit state of collapse, uh, for this case, designing the sections, we use the factored. But for the serviceability check, we use the unfactored or the service function. Yeah, unfactored is because for serviceability also we have certain factors to take. Okay. Using the term unfactored load is wrong. I take back my words. It is you should use the uh, service load or you should use the factors at the limit state of serviceability. We know that the allowable deflection is L by 180. This comes up from the code. The span is 6 meter or 1000 mm by 180, which is 33.33 mm. Now, deflection here under this load is 5 by 384 WL to the power 4 by EI. Now, 5 by 384. How much is the load? Unfactored load will be and this load, this is taking place due to the dead load. So basically it will be this load, but without the factor, which is 3000 plus 250 by 3 to 5 6, around 3 to 5 6. 3 to 5 6. This is in Newton meter. So let's convert it into Newton mm by 1000. Length is 6 meters for 6000 mm. E is 2 into 10 to the power 5 Newton per mm square. And I of the section, is it mentioned? I about the major. I is also mentioned. 839.1 into 10 to the power 4. 839 into 10 to this you will get to be 32.73. Let me check. 3256. I'm done have certain round up here. Yeah, around 32.99 mm. Which is less than delta output, which is fine. So this is how you will design for Nintendo's um, polish. Then then let's use some take a break of about 2 minutes, and then we'll come back with some different. It's straightforward question application of what uh, was discussed in the class today itself. Like we had learned how to calculate the plastic section modulus of the channel section, which is unsymmetrical about one axis, and give you a section which is symmetrical about both the axes. You need to calculate the basically I'll be giving you an I section. You have to pick up the plastic section. Determine the plastic section modulus of ISMP 500 86 metric. This is the weight per meter run about some recap it. So the properties are D is equal to 500 mm, DF is equal to 180 mm, TF is equal to 17.2 mm, and TW is equal to 10.2 mm. And you have these options: 2047, 290, 959, 1694, everything is in centimeter cube. 256.20, 1577.27, 208.26, 1618.40, 276.07. Let's check out the correct answer. 10. If the correct answer is the same. I think so. You can solve this question. It's very straightforward. And move on to a different uh, topic. Not a different topic. That is, suppose you have a situation where I'll write down the question. Steel beams with a clear span of 8 meters are resting on 200 mm wide end bearings. Why is this particular data given? So that you can find out the effective span of the steel beams, which will be the clear span plus half of the effective width from half of the width of the bearing from both sides. So basically, the effective span will be 8 meters plus point 1 meter from the left hand side and point 1 meter from the side. 8.2 meters of the effective span of the steel. This is what wants to be conveyed through the graph. Beam spacing is 3 meters. Beam spacing is 3 meters. And beams carry a dead load of beams carry a dead load of 4.5 kilonewton per meter square. And this is including the weight of the section. Including the weight of the section. And imposed load on the beam is imposed load on beam is 13.25 kilonewton per meter square. And beam depth is restricted to, see, this data is important. It will play a important role later on. Beam depth is restricted to 500 mm, and yield strength of the steel is 250, means 250 MPa, and beam is laterally supported. So first we'll do certain load calculations. From there we'll get an idea about the bending moment. Once we have the idea of the bending moment, then we'll get an idea of the plastic section modulus required. Based on that, we'll select the section, and then we'll check whether the section can take the bending moment. This is what we're designing any kind of section. Here we are concentrating on beam cells. Let's take the load and calculate the moment. So what is the total load? It will be dead load plus the imposed load. What is the dead load? 4.5 kilonewton per meter. Imposed load is 13.25 kilonewton per meter square. So the total load is 17.75 kilonewton per meter square. Now, here it is written that the beam spacing is 3 meters. What does this mean? So, it will look something like this. I'm drawing the plan view. Suppose there are a number of steel beams. This spacing is 3 meters. This is spacing is 3 meters. And this is the length is 8 meters. So it's from roof plan sort of thing. So it is the like the term which I had used earlier. We can call it the total contributory area. So this the load which is coming on this area will be carried by this beam. Like now I'm concentrating on this beam. The load acting on this beam will be coming from this area which I just hatched. Now what will be section? This will be 3 meter. This will be 8 meter. So the total load acting on this beam, let's consider that we want to consider the load as a as let's say I want to convert the load into a UDL. This one. So the load, this UDL will be 17.75 kilonewton per meter square into this 3. So this comes out to be 53.25 kilonewton per meter divided by 8. Now, since you know the UDL, what will be the factored value of that load? It will be 1.5 into this 53.25. So that will be some 80 kilonewton per meter. And this 8 meter was the clear span. So the effective span that, like I explained, it will be 8 plus 0.1 from one side plus 0.1 from other side. So basically, if I look at the section here, it will be something like this beam is resting on two bearings. This is 8 meter and this is 0.2 meter and this is 0.2 meter. So effective span it will be 8.2 meter. This is effective fraction. Okay, this is understood. Now you know the value of factored load. Now simply calculate the moment and shear because so this is the value of load. So maximum moment will be at the midspan. W will square by 8. We are considering this. It's basically this like a simply substitution. So the moment at midspan will be W into L square by 8. W is 80 and 8.2 meters divided by 8. 672.8 kilonewton meter. And what will be the reaction, maximum reaction, the maximum shear force? It will be at the support. It will be W into L by 2, which comes out to be 328. Now, we have to select the section. So we know that to ZP into Fy by command 0. So ZP required will be moment into command 0 by Fy. Now the moment here is 672.8 into 10 to the power 6. Gamma and 0 is 1.1. Fy is 250. This comes out to be 2960.32 into 10 to the power 3 mm3. But when we look at the handbook, as we says, you will find that with this amount of plastic section modulus, and here the depth is restricted to 500 mm, you will not find any section. So you need to take a section which has a depth less than 500, um, very close to it, and then you have to increase the plastic modulus at section. How will you increase the section modulus? It's simply attaching, like what is basically plastic section modulus. Basically, you have to put areas away from the centroidal axis. Why do you need to put areas away from the centroidal axis? Because it is basically the area multiplied by its centroidal distance from the equal area axis. So in the here it's an I section, and bending is taking place in place about the major axis. So if this is the I section, you can simply put steel plates here and here. This will be the equal area axis. And if you put the steel plate at the top and bottom, so the increment in the plastic in the um, plastic section modulus will be area of this plate into it. So in this way, you are will be able to reach this required value of Z, uh, uh, required value of plastic section modulus. So let's select a section ISHP 450. And so the depth is 450 mm, less than 500 mm, so we are satisfying it. And its plastic section modulus is, so let's select ISHB 450 at the rate of 0.907 Newton per meter, and its depth is 450 less than 500, so it's fine. But the plastic section modulus is 203,095 into 10 to the power 3 mmK, which is less than this level, the required that we have. So the balance amount has to be provided by its plate. So, uh, so first we need to get an idea of how much extra plastic section modulus is required. So this plate should additional ZEZ, which we require, will be 2960.32 into 10 to the power 3 minus 2030.95 into 10 to the power 3. So this is 929. So into 10 to the power 3. This much has to be stored. Now, assume that the thickness of the plate is 14 mm. So if you provide 14 mm plates on the both the sides, so the total depth comes out to be around 480 mm. So it's less than 500. So assume thickness of the plate is 14 mm. Assume thickness of the plate is 14. Fine. Now the total, the distance between the center of the plates, like from this mm, from this from this point to this point, from the center of this plate to center of this plate, how much will it be? If the total depth is 478 minus 14, basically it will be 464 mm. So the distance between the center of the plate, this will be required later. So distance between center to center of the plate is equal to 464 mm. Now we know that Z, bracket section modulus, some area into y1 bar plus y2 bar, y1 bar being this, y2 bar in this. This we know this is 464. Area of the plate we don't know. Additional ZPZ which we need can be plugged in here, 929.37 into 10 to the power 3. So the required area of the plate is 2003 mm square. Now we know that the thickness of the plate is 14 mm. So the width of the plate will be 2003 by 14, which is 158 mm. Now width of the plate, it's rounded up to 200 mm. So size of plate is 200 will be width and thickness will be 40. Okay. Now you have to check the plastic section volume. Now, therefore the total ZPZ, first what is being contributed by the I section and the contribution by the plate. Contribution from I section plus contribution from plate. Contribution from I section is 0.0958 into 10 to the power 3, and from the plate is basically area 200 into 14 into the centroidal distance, which is 464. So this comes out to be around 3330 into 10 to the power 3 into 3. And you required around 2900, right? 20, yeah, you required around 2960 into 10 to the power 3 meters. And what you're getting is greater, 2960 into 10 to the power 3 meters. So this is fine, the section modulus. Then you need to check for deflection. Then, okay, let's first do the moment check, shear check, and then we check deflection. So for moment check, oh, that's right. So that will be, it will be that PZ into Fy by gamma. You need to check what kind of section is this. So do we have, okay, I don't have the section properties right now. You need to, I believe it will be either it will be a plastic section or compact section. So ZPZ, which I just calculated. Uh, okay, it will satisfy the moment capacity since I'm satisfying the requirement for see, you calculated the load. Based on the load, you calculated the moment, and from the moment, depending upon the moment, you calculate Z required, the plastic section modulus required, and you're satisfying. So the moment is being satisfied. So there is no point in checking for the moment strength. Right. So let's check for deflection. Now, how much maximum deflection is allowable in a beam? L by 360. So delta allowable is effective span by 360. What is effective span? 8.2 meters is in German by the. So it's 22.7 meters. Now, how much moment of inertia? Uh, Now, this deflection is actually 5 by 384 WL to the power 4 divided by EI. So you know the allowable deflection. For satisfying the allowable deflection, you need how much I is required. So I required will be basically 5 by 384. W will be the total unfactored load coming on the section. What is the total unfactored load? Total unfactored load is this 53.25 or the serviceable load 53.25. This is 5 2 into 10 to the 5. This then delta comes down here. 8 to 4. So this comes out to be check this should be so this load was in kilonewton per meter. So it remains the same in Newton per mm. It's fine. So this comes out to be 68807 into 10 to the power 4 mm. You just need to check whether this I is getting satisfied or not. So for I, which is given here, it will have some contribution from right section and some contribution from the plate. Now for the section, the contribution is 40349.9 into 10 to the power 4. And for the plate, it is basically it will be in the plastic section modulus. Sorry, I will be first about its own centroidal axis, and then we will use the parallel axis theorem. See, for about its own axis, the terms coming up will be 14 cubed into 200 by 12. In comparison to other numbers, this will be really small. So we are ignoring this term. We are just using the parallel axis theorem, which is area of the plate, which is 14 into 200 into its distance from the centroidal axis, which is the depth of the how much is half of 450, which is 225. So half the depth of the channels, sorry, I section, which is 225. Let's have the thickness of the plate. And since there are two plates, one at the top, one at the bottom, we have this one. And this comes out to be around 30,114. This comes out to be around 70,490.9 into 10 to the power 4 mn to the power 4, which is greater than Z required. So deflection is also being satisfied. Then we need to check for shear. The shear capacity of the section is Fy by root 3 gamma and 0 constant into the area d into dw. This is the area which will carry the shear. So 250 by root 3 into 1.1 into 450 into 11. So this number is 0.23 kilonewton. And here, while calculating the moment and all, he had assumed it to be a case of load figure. So this, the shear which is coming on the beam should be less than 0.6 VD. So 0.6 VD is some 400.33, and the shear which you have is 328 kilonewton. So the shear which is coming on the beam is less. So it's a case of load slip, and it's fine. So this is the entire idea of this section. That if there is some depth restriction or basically how do we increase the section modulus of built-up section by attaching nails, how we calculate its section modulus. That is what I wanted to demonstrate through this question. So if you have any specific doubt, free to ask. In the assignment, if you're stuck something, maybe I can ask you. If you have any doubt in a question and you have solved it and you're not sure whether it's correct or not, you are free to drop a mail. I will surely tell whether you are in the correct direction or not. Like through this exercise, even I will get to learn something uh, which might be new for me. It would be a good exercise if you drop the questions in that way. And so that's the we will do a question on gantry girder. And through that question only, I'll touch upon the clauses mentioned in the course. So that is why I did not pick up the topic today because I'll not be able to solve a question today. I don't have the I don't have enough time for modal provisions. Till now, I believe you should be able to start reading the code, right? Even if in the slide certain information has been given, the clause is mentioned, please go to the code and read it. I feel it is a good practice. Okay, if there are no questions, thank you for attending the session. I hope this has added, this experience has added to your. Thank you. I'll be here around for 5 minutes if you have any question. If you don't have any questions, you are free to take. Well, thank you. I'll close.